right, welcome everybody. So we'll talk about fractions and rates that we use in biostatistics and epidemiology. All right. Basic algebra is going to be the important element of this talk, and the two formulas and to equate whatever that we'll be using is this first one, right? When we divide a by a, we get 1. And the basic fact of how we simplify complex fractions, rather than you have a fraction in the numerator and the denominator, you just cross multiply, right? A times d divided by b times c. So we'll see some nice applications of these two fairly simple equations. Here we go. We're going to start talking a little bit about probability and odds, which is basically the crux of this presentation. Probability is just a measure of likelihood that anything will occur, any event of interest. And the formula for it is fairly simple. If we are able to count the number of outcomes in the event of interest, that number is going to be in the numerator, and the denominator will consist of all the possible outcomes under consideration. Okay, that's probability, and it's usually expressed as a relative frequency, i.e. a percentage. Okay, so that's probability, right? Now the odds is very similar, slightly different. They're related, but it's slightly different. The odds in favor of an event is the number of favorable outcomes. So actually this numerator will be the same as the numerator in probability. Okay. How many outcomes do you have in an event? And then you're going to divide by the number of unfavorable outcomes. Okay. So it's a little bit different, right? A little bit different than probability. As I said, the two ideas are related. We'll see in a minute a couple of examples. And this is usually left as a ratio when you just talk about simple odds. We'll talk about the odds ratios, so that's going to be a little bit different. But anyway, okay, so there we go. So, quick example, right? Very simple example that everybody should be able to understand here. We're going to draw one card at random from a standard well-shuffled 52-card deck. And we are asking, what is the probability of drawing an ace? We have 4 aces total, and we have 52 cards total in the deck. So that ratio is going to be 4 out of 52. And as I said, this is usually expressed as either in a decimal form or as a percentage, right? Whatever people feel more comfortable with, that's fine. 7.7% chances of that happening. The odds in favor of an ace is 4, but that denominator is now not 52 anymore, right? Because we have 4 favorable cards and we have 48 cards that are not aces. Okay. So the odds will be 4 to 48 or 1 to 12, right? We can easily simplify those numbers because it may be easier to think about 1 in 12 than 4 in 48. Okay. You're basically saying the same thing, but that's it. And one more example here, right? What is the probability of getting a red card, right? That's half of your deck, right? So that should be 50%. And the odds will be 26 out of 26, or 1 to 1, or 50-50, right? That's how usually people say 50-50 chances of something happening, right? So yeah, these numbers are related, but they are different. They're different. Any questions so far? So those are just some basic things here. Summarizing data. All right, this is what we call the gold standard in statistics and biostatistics, right? Once the data has been collected, and of course, this can take a lot of time to get to this point of the data summary. Right? It may take weeks or months or years, right, to get to this stage. But the gold standard is basically you're looking at 2 variables, right, that you can categorize in 2 ways. Something either happened or something did not happen. So it's kind of very binary. We call that binary variable. Basically, you have 2 categories in each. Something happens, something does not happen. You either got this treatment or wherever you got exposed to something, or you did not. Okay. The simpler the better, right? That's that's the basic idea that's governed behind. And then, of course, in the cells, right, we have different frequencies. So, for example, A, that means what? That means people. That's the number of people who were for whom the treatment was effective, and who were actually in the treatment group. Okay. The most important measures of risk or associations that we'll talk about, the first one is the risk ratio, the sample risk ratio, is the ratio of two probabilities, right? Okay, so it's the probability of outcome in the treatment group, which is A over A plus B. So right here, A divided by A plus B. Okay. So it's what we call this in statistics, that's a conditional probability, okay? Because you're conditioning by the treatment group. Okay. And then in the denominator, you're going to have the probability of outcome in the control group. So it's basically very, very similar. You're going to get C divided by C plus D. Okay, because that's the total number of people in the control group, right? Okay. The sample odds ratio is a little bit different. Very similar but different. Okay, in the numerator, you're going to have the odds for the outcome of interest in the treatment group, which is going to be, as we defined earlier, the number of favorable outcomes divided by the number of unfavorable outcomes. Okay, that's why you see A over B in the numerator, and similar thing in the denominator. Okay, it will be the odds for outcome in the control group, which is going to be what? It's going to be C, the number of favorable outcomes divided by the number of unfavorable outcomes. Okay. And that we can simplify a little bit by cross-multiplying, as we said earlier. So it's just going to be 80 over B times C. It's easy to, the odds ratio is easy to remember. All you do is cross-multiply A times D divided by B times C. That's why people love actually odds ratios, but we'll see later. It's a little bit more difficult to interpret that odds ratio. Okay, when A and C are small, okay, so we are talking about these two numbers in the very first column here, A and C, okay. This is kind of useful. When A and C are small, then the risk ratio can be approximated by the odds ratios, and we'll see an example of that. Why is that the case? But because when A is really small, A plus B is relatively close to B. Okay, so I'm replacing A plus B with a B because A is supposed to be a really small number. Okay, and C plus D will be close to D in the denominator because C is small too. But this, by definition, is the odds ratios. Okay, and this is kind of interesting. This is how the odds ratios are used very frequently. You use odds ratios to approximate the risk ratios if it is difficult to get to the risk ratio, depending on your study design and everything. It gets a little bit complicated, but okay, that's all that we need to know for now. As I said, we'll see an example of this, right, where these two are very close to one another, right, when A and C are small. Another case of the gold standard is when we study the diagnostic or screening test. Okay, then we know that the data can be summarized in this way. TP means for the true positive. FN means for the false negative. Okay, these are the people who tested negative but who actually do have the disease. So those are the false negatives. False positives, you did test positive but you don't have the disease. Okay. And the true negatives. So in any good screening test, these two numbers, the TP and the TN, the true positives and true negatives, those should be high numbers, okay, compared to the false ones. Okay. So that's something to just keep in mind. What's going on? I'm going to start with this here. When the risk ratio, the odds ratio is more than 1, we have a positive association, i.e. what that means is that the treatment or your exposure, right, increases the risk for the outcome. That's how this is interpreted. We'll see that in an example. When either one of these two is less than 1, we have a so-called negative association, i.e. your exposure or treatment reduces the risk for the outcome. Okay. And what we call the bad case is when these two happen to be 1 or very close to 1. That means what? That means that the numerator has to be the same as the denominator, right? That's how you get these ratios to be 1, right? That means that there is no association between the risks in the two groups. Okay, the risk for something will be the same in both the treatment and the control group. Okay, so that's, for the researchers, that's the bad case. All right, we don't want to be anywhere near 1. Usually, okay, because it's a fraction, right? It's a ratio. So, when the two are the same, the numerator and denominator, you're going to get 1, right, or something very close to 1. Okay, we'll see an example, right, pretty soon. The risk ratio is used in both experimental and prospective observational studies. If you don't know what that really means, it doesn't matter right now. The odds ratio is primarily used in observational studies and especially in retrospective studies. Okay. Something to keep in mind, the risk ratio is the ratio of two incidence rates. That's why you really need a prospective study to actually get a good, and a good measure is actually then risk ratio, okay, because it is the ratio of two incidence rates. This does not happen in retrospective studies because you artificially create incidents, okay? Because you start with cases and controls and you go back in time and see who was exposed and who wasn't exposed. Okay, so it's a little bit different, okay? Okay, so here's the first example, right? We're going to look at a new treatment, a new drug for lowering cholesterol, okay? We have two categories, clinically significant reduction and no clinically significant reduction in cholesterol, and new treatment and the old treatment. Okay, so here are the numbers, and we'll see how effective this new treatment really is. Okay, in comparison to the old treatment. Okay. We can get the risk ratio, the sample risk ratio, and it will be what? As we said, it will be 645 divided by the total of our participants in the new treatment. So it will be 645 divided by 800, and in the denominator, it will be 455 over 710, okay, because that's the total for the number of participants who are receiving the old treatment. And when we cross multiply and simplify, we get about 1.258. So the question is now, is this good or relatively good or so-so? Well, that will depend on how you want to look at these decimals, right? So let's take a look at here. So the interpretation is this, right? So people who received the new treatment were 1.258 times, or 25.8%, more likely than those who received the old treatment to show a clinically significant reduction in cholesterol, right? So the question is now, is this 25.8% really good enough for us? Okay. That's usually when biology and chemistry and medical people come into play, and they will tell you whether that's good or not. There's a little bit of improvement, right? But we don't really know exactly what. The next step here would be to actually get a 95% confidence interval for this risk ratio and see if one is included in that confidence interval. Because we are, relatively speaking, you're close to 1. Not exactly, but that will be the next step for us to see, well, is it plausible that risk ratio is 1, right? Because if it is, then the new treatment is not all that effective compared to the old treatment. Okay. Are we okay so far? Another example, same treatment, is it safe? Is it safe? So this will come later in the study, right? Your drug has been on the market for a few months. We still follow a few people, right? And we're gonna go and see how many have developed any serious side effects and how many of them had no serious side effects using this new treatment, okay? And here are the numbers, right? We have 200, 680, and so on. And we're going to do the sample odds ratios because these are usually retrospective studies. So what are we going to do? Well, the number of favorable outcomes is 200 divided by the number of unfavorable outcomes, which is 600, okay? And same thing here in the denominator. Cross multiply once again, and we get 7.556 approximately. Now, that's a pretty high number for the odds ratios, okay? So that's a serious concern. That's a serious concern here, okay? So would we recommend withdrawing this drug from the market? Yes, absolutely yes, because your odds ratio is way, way beyond 1, okay? So, so the odds for the participants in the experimental group of experiencing serious side effects was 7.556 times the odds of experiencing serious side effects in the control group. So it's kind of awkward a little bit. That's why people don't like using odds ratios, because it's a little bit more awkward to interpret that. I cannot really say that these participants in the experimental group were 7.556 times more likely, because I'm not comparing true probabilities. I'm comparing two odds ratios. Okay, so it's a little bit cumbersome to write that out. Okay, but really that's what you're comparing two odds in that odds ratio. So in any case, yeah, maybe the drug should be withdrawn from the market, right? It's a little bit too unsafe. Quite a bit, actually, not just a little bit, but quite a bit. But here's another example, right, with the same thing. We're looking at the same drug, but now what do you observe here? Oh, these two numbers are very small. So if I had that scenario, right, my conclusion would be, well, you know, this new drug is pretty good, actually, when it comes to safety. And we'll see what happens with the odds ratios and risk ratios. We'll see that they're actually very close, and that's what we said a few minutes ago. I can actually calculate, if I need to approximate the risk ratio, I can calculate the odds ratio easily, and this is what I got, okay? And if I wanted to really use the risk ratio for whatever reason, I will get something that's very, very close to the odds ratios. Okay? And this is where people actually interpret the odds ratios as the risk ratios because they're so close. Okay. So now the conclusion is, yeah, the new treatment is really just as safe as the old one, because we are very close to 1, and the confidence interval, if we did calculate it, would include 1 for sure. So this is actually an example where 1 is not such a bad news, right? So we are at least as safe as the old treatment, right? The previous drug that we had, or our competitor's drug, right? If you work for a pharmaceutical company, those are the things that you'll be doing. So we are not any worse than the old treatment, right, when it comes to safety. So here's an example where you want your risk ratio to be less than 1. Okay, flu vaccine, right? We're going to look at people who got vaccinated and who did not get vaccinated, and see how many people actually got the flu and did not get the flu. All right, so here are the numbers, and here are the calculations. If we do the risk ratio, once again, it would be 56 over 434 divided by 100 divided by 420, cross multiply, and we get 0.542. 0.542. So the number is less than 1, so we got to be a little bit careful here how we interpret that, right? What is the reduction rate? The vaccinated individuals were actually 45.8% less likely than non-vaccinated individuals to contract the flu. Okay, so here we subtract. Does that make sense? Yeah, when you buy something and you buy 90% of the original price, the reduction was what? 10%, right? You subtract. Okay. Good, okay? Yeah, so we got to be just careful when these odds ratios and risk ratios are less than 1, then you, in order to actually write the correct interpretation, you just have to subtract minus that. You'll be fine. Now to diagnostic or screening tests, and this is kind of interesting. We know we have a certain number of participants who actually do have COVID-19 and a certain number that does not. And we are trying to develop this new screening test, okay? And we have the numbers here for the true positives and true negatives and false negatives and false positives, and here are the totals. Okay? So we're going to see what we can do about these things. All right. First one is the sensitivity, right? The sensitivity or the true positive rate. Okay? It's just the proportion of diseased individuals who tested positive. Okay? Who tested positive. So what's going to be in the numerator? Well, the TPs, right? Those who tested positive. What's going to be in the denominator? Well, we said it's the proportion of diseased. So what I have to have in the denominator is what? True positives and false negatives, right? Those are the people who actually do have the disease, right? That's why you see that in the denominator, right? Because the proportion of diseased individuals. Okay. And when we plug in the numbers, we get 0.8358. Okay. What does that mean? That means that 83.58% of the diseased individuals tested positive. That's the first step, right? And you've seen that, right, in the class. We talked a little bit, because it's a conditional probability once again. Yeah. Very important statistic that's usually reported when they talk about new screening tests is the positive predictive value, or PPV, is the proportion of individuals with a positive test who actually have the disease. Okay. So now, in the numerator, I'm still going to have true positives, but it's the individual with a positive test. So it's everybody who got positive tests, right? The true positives and the false positives. That's what's going to be in the denominator. And we get 9271. So the interpretation is 9271% of those who tested positive have the disease. That's a very important number, especially when you get tested for anything, right? It doesn't have to be COVID, right? You should be able, and you should actually ask your specialist, what is the positive predictive value? So if my test does come back positive, what's the probability that I actually do have the disease? Okay, and we would like that number to be at least 85%.
You said at least 85?
Mm-hmm. Should be more than that. Hopefully it's more than that. But, there are tests actually that have a much lower value, like 60, 65%. And then if that happens, then your specialist will have to do an additional test. Right? They want to start with the cheaper procedure first and then move on to them. If something, if there's a suspicion that the disease is there, we got to do something else. Okay? But they want to start usually with the cheaper option first. Specificity, or the true negative rate, is the proportion of non-diseased individuals who actually tested negative. So everybody who tested negative will be in the numerator, and we're going to have false positives and true negatives, because those are the people that do not have disease, right? False positive and true negatives, you don't have disease. And we got this number, right? So 95.04% of non-diseased tested negative. Well, that's a good number too. That's a very, very high number. Okay. And another important result is this negative predictive value, or NPV. It'll be the true negatives divided by everybody who tested negative, right? Everybody, false negatives and true negatives, right? And that's 88.46. Once again, that's an important number, right? It's 88.46% of those who tested negative do not have COVID-19. And that's important to know, right? So if my test comes back negative, I would like to know, well, how likely is it that I actually do not have this condition or disease or whatever that may be? That also should be pretty high. Those are the high, pretty numbers. And as I said, your specialist that you see, that specialist should know these things, okay? Or at least they should know where to look it up if they don't know, should you ever have to see a specialist for any kind of, disorder or disease or anything like that. It's important. They should know that, right? If they claim they're a specialist for that, If you refer to this person because they're a specialist, they should really know quite a bit about these diagnostic tests as well. If they don't, find another one. That's what I was told. Accuracy. Overall accuracy is also important, right? So this is not a conditional probability. It's just true positives and true negatives divided by everybody who was in the study, right? Everybody, total, grand total. And this is pretty high, 90.11, 90.11%. So basically the test is accurate 90.11% of the time. It's just pretty good. That's a pretty good test. There will always be a little bit of uncertainty, right, because of how these tests are, manufactured and administered. So there's always going to be, a little bit of leeway here. But anyway, sometimes people want to repeat, just in case. But anyway, and here are the basic guidelines. So for the diagnostic accuracy, you would want to be in these first two categories, right? At least 80%. I would say at least 85%. But anyway, those are very good or excellent tests. Sufficient and good, not really. I mean, I don't know how many tests are really being used that have this lower accuracy. Sometimes, depending on the disease or disorder that you're looking at, sometimes you just don't have, because of the chemistry and biology that's involved, you may be just, okay with what you have, like 75% accuracy. Okay, that's all that we can do. It just depends on what what's involved here. Anything below 60% shouldn't even be used. Okay. Okay. The test is really not that useful at all. A false positive rate, or fallout as we call it sometimes, is the proportion of non-diseased individuals who tested positive, right? So so it'll be false positive divided by false positive plus true negatives, right? These are the non-diseased, okay? And I have to have false positive in the numerator, and that number should be pretty small, right? It's about a little less than 5%, right? So about 5% or so of the non-diseased individuals tested positive. Okay. So that's just another ratio. Another one is the false negative rate, or the miss rate. So we're going to have false negatives now in the numerator, and on the diseased true positives and false negatives in the denominator, right? That too should be pretty small. This is a little bit high, but it's still okay. About 16%, right? 16.42 of the diseased individuals would test negative. Okay. So that's another thing to look at. And this can go on and on and on. Okay, people have written 700, 800 pages books about this. About this little table, 2x2 table that we talked about. Okay, you can talk about this forever. You can easily spend like 2 years talking about this, 4 semesters easily. Okay. Another interesting ratio is positive likelihood ratio. We already calculated these two, so it's the ratio of the true positive rate to false positive rate. And that's a good number to look at, because what it says that the true positives are approximately 16.85 times more likely than false positives. Okay. Well, that's what we would like to see, right? We would like to see that ratio pretty high. Pretty high. Negative likelihood ratio is very similar, right? It's the ratio of false negative to true negative, so it's kind of reversed, right? Because the positive likelihood ratio was true positive divided by the false positive rates, and here it's a little bit different. It's false negative divided by the true negative rate. Okay. That's just the way it's defined for certain other reasons. But anyway, whoops, I should not be there yet. Okay, so so we already calculated these two numbers, and this number should be much less than 1, hopefully. And this is telling us what? This is telling us that the false negatives are about 82.63% less likely than true negatives, okay. Which is good news, right? That's what we would like. You would want these false negatives not to be very common occurrence, right? We would hope. Okay. And the final one is the diagnostic odds ratio, and that's the ratio of the two likelihood ratios. And this number, according to what I was told, should be always more than 1, preferably more than 20 if it's a good test. People do not actually interpret this, but they simply look at this and see, okay, if it's, if it's a decent size, you have a good test on your hands here. So we want this DOR, or the diagnostic odds ratio, to be greater than 1. Higher the DOR, the better the performance of the test. Okay, so in this case, for this particular diagnostic test, this is very good news. Okay. If you're a researcher and you figure this out, yeah, okay, you can now report, we have a good test. We can start asking for approval, right? So that you can market it and you're ready to go. Okay. Any questions so far? I'm kind of going fast, but.
So a couple slides back.
Mm-hmm.
Right there.
Mm-hmm.
One more. The other way, sorry. When you had the 4%.
The what? Oh, here,
Right
right?
here.
Uh-huh.
So sometimes you hear them say, plus or minus 4.
Oh, that would be the margin of error, right?
Margin error. Is that applying here? Or is that
Only if you want to, yeah, because only if you're calculating the confidence interval for this rate,
okay.
which you could. But this rate will always be a positive number, because all the numbers here are positive.
Oh, okay.
But if I want to get the margin of error for the population false positive rate, then I would get plus minus, because I would then subtract and add that margin of error to this estimate to see where the population false positive rate would fall.
Okay.
Yeah,
Thank
that
you.
would be the next step
That would be the
to
next step.
get that confidence interval, and then you would get margin of error, right? Plus minus whatever.
Okay.
So the margin of error could be here. I'm guessing maybe plus minus 2% or something like that.
Okay. Thank
Something
you.
like that. So where were we? Oh yeah. So we talked about. So yeah, this is pretty good. Sometimes a perfect diagnostic test, which can happen. That means that some of your cells will have zeros. Okay. So I have no false positives, no false negatives. I cannot leave those as zeros because I cannot divide by 0. Okay. So the correction, right? The correction is to actually put 0.5 in those cells for false positives and false negatives, if that happens. So that you can still actually calculate all your rates and things like that. It's just called continuity correction. Okay. Because otherwise you're stuck. You're not going to get any finite number, right? If you have to divide by 0, or if you have 0 that divide by 0, right? You're not going to get anything. So, okay, and this is it. And this is a fun video, right? If you wanna watch, this is kind of interesting. I showed that once before 3 years ago in our first year seminar colloquium. Yeah, the sound is kind of bad. I don't want to do it here but you can click on it. Yeah, we want to see what is the difference between neurologists, pathologists, and epidemiologists. I like this because these people, they have clean work. It's very clean. All they deal with is numbers and estimation. That's it. You don't have to take any samples. You don't have to look at dead bodies or,
See, it's not too late to change majors. Epidemiology, here we come.
All right. Any questions? So it's 12:50, more or less.
That was great. Thank you.
Mm-hmm.